And today we will see in detail the three pictures in quantum mechanics. That is Schrodinger and Heisenberg and Dirac pictures. Each picture has its own significance. We will see what are the importance of these three pictures. First, we will take the Schrodinger picture. In Schrodinger picture, the operators stay fixed while the quantum state or state vector changes with the time. This is about the Schrodinger picture. Basically, this Schrodinger picture called as wave mechanics. We are dealing with the wave function rather than the operator. So, once you know the wave function, we can find the probability at a particular time and dynamics of the particle, where it goes and what is the probability, everything about the particle we can study from the wave function. So basically it is wave mechanics. Let us say the initial state vector is equal to get psi of t naught, that is at a particular time t naught. Then in order to find the wave function at any other time psi of t, we can use the time evolution operator u of t naught. When u of t naught act on the initial wave functions psi of t naught, you will get psi of t. So this time evolution operator by definition is equal to, which I have shown in yellow color part. U of t naught is equal to e power minus I h t minus t naught over h cross. This is the time evolution operator. Remember that I have given several lecture on time evolution operator. Evolution operator is a unitary operator. That means it will not change the norms of the function. So that is very important. Then what is the expectation value of operator A sub S? This sub S indicate the Schrodinger picture. In wave function, in Schrodinger picture, the operator stay fixed. I have mentioned here. That means the operator is independent of time. Only the wave function depends on time. Then how this time comes here? Particularly the time derivative of the operator A sub S is equal to, naturally this is time independent one, there is a question mark. However, you can see I have referred time at outside the expectation value. It has its own meaning. Everything in physics has its own meaning. So here also, this is though the operator is independent of time. What about this expectation value? By definition, this expectation value is the inner product of the wave function with as, that is pra psi s t, as gets psi s t. So here this wave function depends on time. So naturally the expectation value of operator as naturally depends on time, as the wave function depends on time. That is very important point. Now what I am going to do is I am going to use the time evolution operator. What will happen when time evolution operator u of t naught act on psi of t0, then you will get psi of t. Similarly, in pra vector, in the case of pra vector, you have to take complex conjugate of this one. That is, u become u dagger. So u dagger u dagger of t naught. Here you have t naught. This is the expectation value of the operator in Schrodinger picture. So we will see this in detail. We have seen the expectation value of operator A in Schrodinger picture as this. Now what I am going to do is I am going to keep T naught as 0. Here also 0. So naturally psi of S T naught, I am replacing it by psi sub S 0. sub a sub 0, here pros 0, here get 0. Then what about the time evolution operator? In the here in the time evolution operator, I am keeping t naught 0, so this will become 0. So naturally, u of t is equal to e power minus I h t over h cross. So now I can replace it. This is psi of 0. U is e power minus I h t over h cross. Then naturally what is u dagger is a complex conjugate of this. This minus become plus e power I h t over h cross. So this is the expectation value of operator in Schrodinger picture. Now we will see the time derivative of this one. Now we will see the time derivative of the operator in Schrodinger picture. So time derivative of expectation value, because we have seen that the operator in Schrodinger picture is independent of time. However, the expectation value of the operator is depends on time. So the time derivative, we are taking the time derivative of the expectation value of the operator A sub S, which is equal to the time derivative of this. By definition, the expectation value of AS is equal to psi sub S of t. AS gets psi sub S of t. Now you differentiate this with respect to bra vector. First you differentiate the bra vector. Then you differentiate this AS. This operator does not depends on time. So there is no explicit time dependence with the operator. So this partial derivative of the operator with respect to time is 0. You can ignore this. Unless otherwise it explicitly depends on time. So first I have taken the bra vector, then I ignored this operator. Third one, I am differentiating this with respect to the get vector. So I'm first I will find the derivative of the bra vector. This bra vector. You know, here of course we have ignored, as I said, partial derivative, time derivative of AS. So this bra vector t psi over tt. From the Schrodinger equation, you know I h cross t psi by tt is h psi. Now you bring this to the right hand side. What will happen? The time derivative of the wave function is equal to 1 over I h cross h psi s. That's what I have replaced here. Since remember that is a bra vector, I used a negative sign. I have to take complex conjugate of this one. So in the case of get vector, what will happen? This is 1 over I h cross, this h will come. Here minus 1 over I h cross, this h. So now you can take 1 over I h cross as common. So I have taken 1 over I h cross as a common, and I am taking the positive value first. That is the bra vector and get vector also same in both the cases. That is in the first term as well as in the second term. Bra vector and get vector are the same, so I am taking bra vector and get vector outside. Then what about this? I am taking this plus sign first, that is ASH first, then minus HAS. So what is AS minus HAS? Is nothing but commutation of A with H, commutation of AS with H. So the time derivative of the operator in Schrodinger picture is equal to the expectation value of the commutation of that operator with the Hamiltonian. That is very important. Here important is if A and H commute, it will be 0. That is, uh, this is operators stay fixed, or otherwise we can say it is conserved. So that is very important point. Now we are going to see the Heisenberg fixture, in which in that we are going to prove that this picture does not matter. So whatever picture you are taking, no physics will change. That we are going to see in Heisenberg picture. Now we will see the Heisenberg picture. The major difference between Schrodinger picture and Heisenberg picture is, as I said, Schrodinger picture based on wave mechanics, whereas the Heisenberg picture based on the matrix mechanics. Matrix is abstract of the physics. You can learn physics through mathematics. The Heisenberg matrix method, I can quote few examples. That is Pauli spin matrix. It is related to observable. Here in Heisenberg picture, we are keeping observable or changes with time. That is observable in quantum mechanics is operator. Operator changes with time. This is matrix mechanics. For example, in harmonic operator, this creation and annihilation operator comes under matrix forms, and Pauli spin matrix and angular matrices are comes under the Heisenberg fixture. In Schrodinger picture, we have seen that operator are fixed, only the wave function changes with the time. Here, operator changes with the time. You can see operator changes with the time, while the quantum state or state vector remain fixed. In Schrodinger picture, we have seen the expectation value of operator is equal to psi sub s t as get vector psi sub s t. Now you make t as 0 by using time evolution operator. So you can change this to any other time by when the time evolution operator act on the wave vector, then it will give the wave vector at a particular time t. Here it is wave vector in get notice. In pra, it will become complex conjugate. That's all. So here it also psi sub s also equal to 0. Psi sub s of 0. So from this it is clear that the wave vector, that is get vector in Heisenberg fixture, H denote Heisenberg fixture, is by definition is equal to the wave vector in Schrodinger picture at the time t equal to 0, because this Heisenberg wave vector is independent of time. So it is equal to both are equivalent. So Schrodinger in Schrodinger picture, psi s of 0 is equal to the wave vector in Heisenberg picture, because it is independent of time. Now what will happen to the terms, these terms? This is a unitary transformation which will not change the norms. And the time factor is taken care of this time evolution operator. This can be written as a sub h of t, that is operator which depends on time, which is equal to e power I h t over h cross a sub s e power minus I h t over h cross. Here it is a function of t. What will happen if t equal to 0? When t equal to 0, exponential e power 0 is 1. So this will simply become as. That is the operator in Heisenberg fixture at the time t equal to 0 is exactly equal to the operator in Schrodinger picture. So it is clear from this. And also, one interesting and very crucial point is, let us say this is any arbitrary operator. This one is any arbitrary operator. Let us take AS Hs, Hamiltonian operator in Schrodinger picture. AS equal to Hs. What will happen? See, in the exponential term, you have Hamiltonian operator only. So Hamiltonian operator will commute with the Hamiltonian operator. So you can bring this uh, back and forth. So in this case, you are not supposed to bring here. So you are not supposed to change the order of the operator here, because we don't know whether AS is commute with the H. Here you can do that. So e power minus I h t over h cross into e power minus I h cross t over h cross will become e power 0, which is 1. That means the Hamiltonian operator in Heisenberg picture is equal to Hamiltonian operator in Schrodinger picture. In fact, the Hamiltonian operator is the same, will not change in any picture. That is very, very important point. We can note it. So now we will see the time derivative of this Heisenberg operator. Now we can see the time derivative of the operator in Heisenberg picture. We have seen a sub h of t is equal to e power I h t over h cross a sub s e power minus I h cross, h t over h cross. Now what will happen if t equal to 0? Then that is a h of 0. T is 0 we have taken. So this exponential term e power 0 is 1, e power 0 is 1. So this will be simply as. So what I am doing is I am replacing this as by ah of 0. So we have taken this idea and I have replaced as by ah0. Now I am taking time derivative of this operator. In the earlier case, that is in Schrodinger picture, I have taken time derivative of the expectation value of the operator, because the operator is time independent. So yeah, however, the expectation value is time dependent. Here this operator itself time dependent, so no problem, you differentiate this. First you differentiate the exponential term left to the this operator a, then it will become I over h cross I over h cross h, then this exponential term appear as it is, and ah of 0 e power this will come as it is. Then what I am going to do is I am going to do the second term derivative of this term operator. This is independent of time naturally, because ah of 0. So you can ignore that. Then you can take the time derivative of this exponential. What will happen? You will get to minus I h cross h. I am using h here. This h I can keep here or here. That is no problem. Here or here, no problem, because h will commute with h in the exponential term. But you are not supposed to bring here before a, because we are not sure whether Hamiltonian commute with this operator a or not. So I can safely keep h here, because I am differentiating this negative exponential term. Now we can simplify this. How to simplify this? See, what happened to this term? Except h, you leave the Hamiltonian. What about this? You compare this and this, that is the ah of t. What is ah of t? is nothing but this one. This is nothing but a h of t. So I have replaced that as a h of t. Then what about this? Uh, Here also this is a h of t. This also a h of t. Now what I am doing is I am multiplying and dividing by I here as well as here. I into I, you will get I squared. So I squared is minus 1. Here I into I squared is minus 1, minus of minus, you will get plus. So I can take I h cross, 1 over I h cross. I will take this positive term first. So A sub h of t h Hamiltonian minus this second first term will come into second place because it's a negative. I am taking the as second term. So this will be minus 1 over I h cross h A sub h t. So I can take I h cross outside, then first term is a of t h minus h a t. This is nothing but commutation of a h with Hamiltonian h. If there is any explicit time dependence on a h, you can add this term, partial time derivative of a h. But naturally this we have taken t equal to 0, otherwise it will be 0. This is called equation of motion. This is used to find the equation of motion. Still our discussion is not over. We will see some of the interesting things. So we have seen the time derivative of the operator in Heisenberg picture, which is equal to 1 over I h cross commutation of A h with Hamiltonian. And this partial time derivative of the operator we have ignored. As there is no explicit time dependence, we have ignored this. So, what will happen to the expectation value of this time derivative of the operator? Naturally, this will be 1 over I h cross. I am taking common. The expectation value is naturally the inner product. So, which is equal to pra psi h, the commutation of a h with h, and get psi h, psi sub h. What is the time derivative of expectation value of the operator in the Schrodinger picture? That we have seen 1 over I h cross, the bra psi x, the commutation of as with h, and psi of gets psi s. So you compare these two. Both are exactly same, except one difference. This is since this operator is time dependent, we are taking the time derivative, then we are taking expectation value. Since it's independent of time, we are taking the time derivative of the expectation value of the operator. Both are same. So by changing the picture, no physics will change. So physics is same for both the cases. That is very interesting observation. So you can use either Schrodinger picture or Heisenberg picture. Nothing will happen. In addition, I will stress that point. We have seen that the operator in Heisenberg picture at time t equal to 0 is equal to the operator in Schrodinger picture. Similarly, we have also seen that the vector psi of h is equal to psi of s vector in Schrodinger picture psi of s at the time t equal to 0. This also we have seen. In addition, we have also seen that the Hamiltonian operator in all the pictures is same. That is h of h is equal to h of s, which we can generalize as h. Hamiltonian will commute with all other Hamiltonian. It is irrespective of the picture which you are using. Uh, then in the next class we will see about the interaction picture. Thank you very much for watching my video and supporting me continuously. Thank you very much.